The next talk we have is from Rohit and Bin on optimizing latency-sensitive queries for Presto DB. Let me give you a quick intro to our speakers. Bin Fan is a founding engineer as well as VP of open source at Alluxio. Prior to Alluxio, he worked for Google to build next-gen storage infrastructure. Bin received his PhD from Carnegie Mellon, and it was in design and implementation of distributed systems. He likes hiking, cooking, and playing video games in his spare time. Thanks for joining today, Ben. And Rohit is a software engineer at Facebook. He is working on latency-sensitive queries for Presto and has a decade of experience in distributed systems. In his spare time, Rohit likes to, it's all about sports, turns out, watches all kinds of sports, plays tennis, soccer, cricket, racquetball, badminton, and video games. Thanks, folks, for presenting today. Over to you, Rohit. You may be on mute. Yep, we can hear you now.
1 second. Yeah. I think 1 second. I'm gonna share my screen. I have like too many windows. I get lost where it is. Right? Can you guys see my screen?
Yes, you can go into full screen mode. Thank you.
Okay. That took some time. Sorry. So Rohit, as Deep introduced me, thanks for the wonderful introduction. I and Ben would be talking about how we optimize latency sensitive queries at Facebook with collaboration with Alexio. So here's the agenda. I'll briefly talk about the overview and talk about the architecture and the problems which we were facing with it. I'll also talk about like how we re-architecture and solve those problems. I'll dig deep into some performance and the benchmarking we did at Facebook. And then Ben would take you over the Alexio deep dive and our collaboration and some of the work we did together. Okay, so Facebook, at Facebook Presto, so let's talk about like the scale we are dealing with in Facebook for the Presto. We have roughly around 40,000 servers. The Presto roughly scans around 1 exabytes of data every day using Presto. Apart from the analytics workload, we have a bunch of ETL jobs, and most of these ETL jobs are scanned using Presto in Facebook. Let's talk about the architecture. So this is a simplified version of Presto architecture. It doesn't really cover all the components of it, but let's focus on some of these things. So as we know, like Presto has coordinators and the workers. In the coordinators, we have planner, optimizer, schedulers. So when a SQL comes to the planner or optimizer, it talks to Hive meta store to get the partitions info. And using these partitions info, it basically builds an execution plan and give it to scheduler. Scheduler then access the file information from the HDFS, and with this execution plan, it breaks the plan into plan fragments and give these plan fragments along with the splits information to the worker. When the worker receives these plan fragments and the splits to execute, it accesses the HDFS to access the data source, data information, right? And using that data, it processes these plan fragments and produce the results and give it back to the query back. Now, this architecture is great because the workers do not have any storage associated with it, which they are completely computation nodes, which means we can scale computation and storage independently. As we have seen, like the peak and non-peak traffics are mostly different, and our computation capacity and storage capacity comes and goes as we need it. Now, this architecture, while it's great, it has its own problems as well, because the worker, for every data need, it has to scan data from the remote and remote HDFS data source. which is a problem for a query engine inspiring to be interactive, inspiring to be like an interactive query engine. So if we want to achieve low latency queries, we need some data locality with it. And that's what we did. I'm like, so when it comes to re-architecture, we implemented data caching. Data caching needs no introduction. It's basically a common optimization technique, which brings the caching, which basically brings the working data set closer to the compute node. And the idea is like if with lesser trips to the remote storage should help out with latencies, efficiencies, and IO scans as well. Okay, so let's look into the new architecture with data caching. So it has multiple parts, but let's focus on the parts which I have highlighted with red. So data cache along with the local SSDs. So with this architecture, our worker had a local flash available with each worker. And we plan to use this local flash as the data cache. So when the worker needs some data from worker needs some data to process, it accesses the remote HDFS and then stores that data into the data cache. Hopefully, when the new request wants the same data access, it looks into the cache, and if it finds it, it returns, it uses that data and avoids a trip to the remote data source. With this, we hoped that we would be able to save a lot on the query latencies because these queries, some of these queries in accumulation are accessing like petabytes of data with no access patterns. Uh, One other thing is I talked about earlier, like our scheduler, when it distributes the workload to different workers, it divides them randomly. When I say randomly, it means it distributes the workload so that the workload is distributed equally among the workers, so that no worker is super busy and the other workers are relatively free. The workload is distributed uniformly, but that is a problem when the data caching is a concern. Because let's assume if a same split gets assigned to worker one for the first execution, the worker one would end up caching that split in its local flash. But if the same next execution come for the same split, and if it gets assigned to worker two, uh, then the worker two would not have any information about this data cache. So it will end up reading from the HDFS again, and it would cache up again. Um, so which means like the same split might get cached into multiple workers. With limited data caching availability as the storage, because we cannot really have too much flash used with multiple workers, we need to make sure like the data cache is effective and we use the cache storage effectively. So we ended up building soft affinity. So what does soft affinity scheduling is? The soft affinity scheduling is basically the scheduler makes the best effort to assign the same split to the same worker. What it means, let's talk in the next slide. Uh, thing we talked about, like earlier, we used to have a random node scheduler. It's not really random. What it means is basically it's the scheduler is trying to distribute workload evenly. But from the data locality and affinity perspective, it becomes random, means the split gets processed by a random worker. But with affinity scheduling, we try our best to assign the same split to the same worker. And the algorithm which we are using at this moment is fairly straightforward. What we do is we take a split, we compute the hash of it, and we find out the which worker should process that particular split. So the next time when the same split is seen again, it is assigned to the same worker. And that's how the affinity is built. Obviously, like when we are assigning the split to the same worker, we always check if the worker can take an extra workload or not. If it not, we assign it to the next worker. And the data affinity may not be met in that particular case. As we can see, this particular algorithm is fairly simple and can run into a problem if worker node goes down or the extra capacity is added. We are working on next generation affinity solutions, like using algorithms like consistent hashing or all, so that we can take dynamic capacity into consideration when soft affinity is considered. Next thing. So how did we build this data caching for our use cases? Uh, we have variety of use cases. Our use cases includes like AV platform, experimentation platform, dashboards, analytics, and a bunch of other use cases. So we do have like Facebook, some of the internal caching libraries, which are great, which are technically rich and offers whatever we need. We were also looking at the open source solutions, and we were also thinking of building one our own because we understand the loads and semantics and dynamics of it. While Facebook internal caching libraries are very good, but they didn't really work great for us because they are in C++ and they are not open source. With our affinity to open source community, we were strongly leaning towards using open source. But to understand our workload and use cases and requirements, we started by building our own. We built file merge caching first. It's a very naive solution. What it was doing is basically copying the remote storage files into the local storage as the workers were accessing them. And some of these files sizes were really small because the data access request was small. We were also merging them to make them bigger and keeping the file count low. This solution worked great for us for a couple of use cases, but for the use cases where we needed to access petabytes of data and where there was no access pattern, it struggled. And this can be seen in the cache rate, which we generated with this solution. As you can see, like the cache rate is up and down all the time. Uh, what it means is basically not only we are seeing the cache miss, but this could have a detrimental effect to the performance of Presto queries, because not only you are reading all the time from the remote data source, but you are also doing the extra work of writing to the cache storage. Uh, Nothing to say, like we didn't really see much improvements for this particular use case, but it actually regressed. Okay, so at that particular time, we started talking to the Alexio, and we had some of our own learnings with this experiment. And Alexio offered most of all these features which we were looking for. But one of the problem with Alexio at that particular time was that Alexio solution, caching solution was available as a service. And we really wanted to use something embedded so that we can avoid an extra hop of using a service. Some of the other things which we wanted was like, we wanted like a Java based open source library. We wanted the segment based caching. What it means is that we wanted to read, write, and evict in the smaller block units like an MB or 2 MB. So because we noticed that that kind of solution would be effective for our needs. We wanted pluggable eviction policies. We wanted different kind of configuration regarding resource usage, and we wanted like asynchronous operation. We wanted like throughput limiters so that we can avoid endurance issues on the flash, and bunch of other things. So we worked with Alexio, and Alexio were very keen on working with us and providing an caching library for us, and our collaboration was great, which is reflected in the performance numbers which we have. So we benchmarked this for one of our use case, and we used a cluster size of 600 nodes. We shadowed some of our production queries to this benchmark cluster. We configured around 460 GB per node of flash for each worker. We configured it with LRU eviction policy. We also used 1 MB as the block size, as we talked previously, as a segment size. which means all of our operations were reading, storing, and evicting in 1 MB size. Okay, so when we executed these tests with Alexio data caching, we were able to see remarkable 48% improvement in our query latencies. This is the P95 number. P75 was around 54% improvement. And this really helped us taking Presto towards an interactive query engine with sub-second of latencies. We also saved a lot in the IO savings. As we can see for this particular benchmark run, we were saving around 57% of data. When it comes to cache rate, as we can see, we achieved a fairly picture perfect cache rate. There were like some dips that can be explained with unexpected queries scanning a large amount of data, and it's not even a frequent query. This illustrates like some of the work which we need to do is to understand the heuristics and be able to avoid caching these queries, which disturbs the whole cache effectiveness. So at this moment, we are using Alexio in Facebook productions for multiple of our use cases. I think it has been live in Facebook use cases for 3 of the use cases. A couple of them also we are working towards productionizing it. I think at this point, we'll take a deep dive into the Alexio with Ben. I'll let Ben talk on this.
Thanks, Rohit. So from this part, I want to give you a little bit more details on what we do for this collaboration and what Alluxio is, if you're not aware of. Alluxio is open source data orchestration system. It's a new layer sitting between the compute and persistent storage in the data processing stack. Alluxio is commonly used to speed up the OLAP queries for engines like Presto, Hive, or Spark, as well as the AI or machine learning jobs for engines or frameworks like TensorFlow or PyTorch. Next slide, please. Alluxio is originated from UC Berkeley AMP Lab as the research project named Tachyon. It was open sourced in 2014, and the top contributors, including the creative company, to continue support, grow, and commercialize this open source technology. And it is backed by the top investors like Andreessen Horowitz. And today we have more than 1,000 GitHub contributors across the world. Next slide. Alluxio has been widely adopted by hundreds of different companies over the world in production across many different sectors, from financial services and retail and technology, internet. You can see from the previous slide. So in here, Alluxio, in this slide, I want to show how people typically deploy Alluxio. It's often used as co-located with or close to the compute process, but with different storage on-premise or in public cloud mounted into this Alluxio namespace. So in this way, user can access the data without noticing the real or physical backend physical storage, which can greatly simplify the development and evolution and maintenance for the data platform, in addition to the performance benefit. Next slide, please. So Alluxio itself is a full-featured distributed file system, but for this particular talk, I want to focus on the collaboration, which is we do with the Presto developers at Facebook to integrate Presto with a local library version of Alluxio embedded into Presto workers. So this Alluxio local cache provides a HDFS compatible interface to Presto worker backed by the external storage in Facebook. And the local library is used to a local directory on SSD or some other media you choose can be used to store the cache data. If it's cache hit, this will serve data from the local cache storage. If it's on the cache miss, this Alluxio caching file system will, on behalf of the Presto, to fetch data from external storage and insert this back to the local cache storage for the follow-up reads. Next slide. Here are some technical details when we are implementing this local cache version of Alluxio. And it is particularly informed by the Presto workloads or the workloads we see in the Facebook. For example, we have to work with the non-sequential read pattern commonly see for the ad hoc queries. And we choose to use a fixed sized segments we call pages in the Alluxio to store. We also store these pages off heap rather than in the Java heap memory to reduce the GC pressure. Also, because Presto is designed to be highly concurrent, multiple threads are doing the jobs at the same time. So we implement the very lightweight but very high performed, highly concurrent thread safe locking scheme to protect, to coordinate among different threads when they're accessing this local cache store to get data. So this turns out to work pretty well with a very minimal storage overhead and computer overhead. And we also introduced some, I think this is very useful features, including pluggable cache replacement policies with LRU as the default one, and also LFU as the optional. This cache library supports different storage engines, including storing data using local file system, and also a more advanced store based on RocksDB. And in order to handle the bursty cache inserts, we also support async cache writes, and we will queue the cache inserts into a data structure and also perform inserts in the background. Also with the performance metrics, you can easily see how it is performing across the entire cluster. Next slide. Yeah, so there are some ongoing work together with Facebook, including support the table level, partition level, and schema level cache quota. And we also implementing an in-memory page store to sustain really, really high concurrent and also low latency requirement. In addition, we also plan to work on the semantics aware caching to further reduce the overhead or get a better understanding of the data so we can provide caching services better. Next slide. Yeah, so this is in a high level, how you can enable this from Presto. It's very simple. And if you want to get more detail, so in here, you just set the cache type to be Alluxio in Presto, and also specify a cache-based directory. If you want to have more details, there is a blog written by me and also Rohit and with some other people in the project. So you can access the blog in the link here. Next slide. Yeah, this is my last slide. If you want to really access more functionalities in addition to the ones from the previous local cache, here is the list of the advanced operations and policies you can implement with Alluxio file system, including fine-grained control on the working set and metadata caching, syncing, data transform, data migration, and some more familiar file system CLIs. So you can control this from the cluster-wide, control the data from cluster-wise. And you can go to our documentation to see the overview. Yeah, last slide. Yeah, I will stop here and I and Rohit, we can answer questions. So this is you can see the recording of this talk and also go back to the blog I mentioned for more details.
Great, thanks guys. Ben and Rohit, thank you for the session. We have a few questions that are coming in. The first question is the library version of Alluxio open sourced as well?
Yes, it is open sourced and has been merged into Presto 236. Maybe Rohit, you can just correct me. Sorry, 0.206.
Yeah, I think the Facebook, it's available with 0.26.
Yeah.
Okay, thank you. A question from Frank, is the Presto soft worker Affinity open source? I think this is similar. If yes, which config controls it?
So there is a configuration called Node Affinity. You can set it to soft affinity. This configuration has been mentioned into the Presto DB blog, which is present, which is in your screen. So if you go to Presto DB.io and look for blogs, you will see all these configurations, which can potentially impact data caching and along with soft affinity as well.
Great. We have time for a couple more questions. So the next one is, with reference to soft affinity scheduling, how do you guard against hot splits? In other words, for hot data, too many tasks could be scheduled to the same worker nodes, resulting in spike in latency.
Correct. So that's why it's called soft affinity. The trick is in the soft. So we try our best to assign the split to the same worker. But if the worker is already processing too many splits, we just move to the next worker. We do not overload the worker. So in those cases, the cache hit might get missed because that particular worker would not have this data caching available, for that particular split. But we go like a 2-level deep. So we have this concept of primary and secondary. In the interest of the time, I didn't really talk about it. So we find our preferred worker and we assign this. If the preferred worker is busy, we give it to the secondary worker. The secondary worker also caches the split. So if the secondary worker gets a job, that the data caching for that particular split would be available in the secondary. If the secondary worker is as well as busy, then we choose the least busy worker, and that particular worker would not have the caching, and we would instruct the worker not to cache that particular split because that worker is not the preferred worker for that particular split.
Great, thank you, Rohit. And let's take one more question from Alec. He asks, it's a question about both the sessions that we have today. Does Alluxio integrate with Hoodie in any way? That is, can Alluxio refresh the cache based on changes tracked by Hoodie? And I'd say it's a good question for future improvements, but Bin and Sudha, either of you, maybe both of you can talk a little bit about it.
Yeah, I will first speak because I happen to work with the community to support Hoodie or Hoodie to support Alluxio. So yes, so I think like should be in the latest release, Hoodie should work with Alluxio. This is some contribution from a startup I talked to, and they are already running Hoodie with Alluxio to cache Hoodie tables on Alluxio. Yeah, but like in terms of whether you can automatically detect the change from Hoodie tables or Metastore, tell this and invalidate the cache from Alluxio. I don't think the integration is there, but like Alluxio can detect a change from HDFS actively, preactively. So as long as like that happens, I think that can work too.
Yeah, thanks, Ben, for answering that. I don't have really much to add on to what Ben said. He really captured it well. But it's definitely some future work that we could research into.
Yeah, so let's chat offline and let's lay down the roadmap for that.
Yeah. Sounds good. Sounds good. If you can stop sharing, Rohit. Thanks, everyone. There were a few questions that we didn't get to. If we haven't been able to get to your questions, feel free to jump onto our Slack channel. It's slack.prestodb.io. I just sent it out to the chat as well, so you should be able to see that. Really excited to have our speakers today. Thanks so much again for your time and your sessions. We will be sending out more information about PrestoCon. Again, save the date as September 24th. And it's an all-day virtual events, more details to come. And finally, if you have feedback on sessions, topics that you want to hear about, or you want to present at our next meetup, do send us a note, feedback@list.prestodb.io, and we'd love to hear from you. With that, we're at the top of the hour. Thanks so much, everyone, to our speakers and our attendees for today's session. Have a great weekend. Take care. Bye-bye.
Thank you.
Yeah.